Another way to test convergence or divergence is to compare it to another series that we can find convergence or divergence pretty easily. And there's two of them. One's called a direct comparison test, one's called a limit comparison test. The idea is that you're going to compare it to a series that you already know information about because they behave very similarly in the long run. Like if you look at this series, we know that this is a geometric series and it converges because r is equal to 1/2. This is not a geometric series because we put that extra n there. But what we can do is start comparing these two. Similarly, this is a p series which we know it converges. This looks very similar, but it's not a p series, but we can compare the two. Right? So let me do two examples first, and then we'll kind of draw the conclusion. So when I give you this series, this is not a geometric series, but what you want to look for is a series that's kind of embedded in there that looks very similar to something that we can work with pretty easily. So I see that there's a geometric series in there, 1/2 to the n. And I know in this case, this is a geometric. Your r is 1/2, so we know that it converges. Okay? And what you're going to do is you're going to compare each term in that series for n equals 1, 2, 3, all the way to infinity. So what happens when you add 3 to the bottom of a fraction is it makes the bottom bigger, but it really makes the whole entire fraction smaller. So 1/3 plus 2 to the n is always going to be smaller than, or it can be equal to, 1/2 to the n for every single number. So if that's true, if you have something that converges, the conclusion that we can draw is that anything smaller should also converge. That's the idea. Okay, let's try 2 more examples all the way through. So look at this series. Notice that there is a p series embedded in there. So this is a p series that diverges. So that's the first thing. Identify the series you're going to compare it to, tell me what happens and why. We're going to compare the numbers. So try to figure out what's the comparison between this and this. Well, when you subtract the number to the bottom of a fraction, it makes the bottom of the fraction smaller, but it really makes the whole fraction bigger. So for every n from 1 to infinity, this is always going to be bigger than this. So if anything diverges, the conclusion is anything bigger should also diverge. So this diverges by the direct comparison test. So show me the series you're comparing to, show me the inequality, and then you can draw the conclusion. Let's try one more. Okay, look at this series. You see there is another p series that's embedded. So first thing is, let's figure out what's happening to this. This is a p series that converges. Now I want to compare each term in that to the original series. So again, I'm adding a number to the bottom, which makes the bottom bigger, but it really makes the whole fraction smaller. So this is our inequality. So if you have something that converges, then anything smaller will also converge. So it's true that this is going to converge by direct comparison tests. And that's what this is saying. There's no card that you will make on the direct comparison test. So let's say you have two series. A sub n is always the smaller one, B sub n is the bigger one. So if you have something that converges, then anything smaller will also converge. If you have something that diverges, anything bigger diverges.